Hey y'all, what's up? Coach Hyde, coming to you. Gonna try something a little different today. You got a reading from our book, A Short History of Nearly Everything, with Bill Bryson. So what I want you to do is, when we're going through the book, I want you to follow along with me. We're gonna stop throughout a little bit as we look at our signposts that we come across as we go, and take a look at those, and then we'll dive back in the book. So we're on page 140. We're at the second paragraph where it says, "Let us pause for a moment." All right, so find that and follow along with me in the text. So, all right, let us pause for a moment and consider the structure of the atom as we know it now. Every atom is made of three kinds of elementary particles: protons, which have a positive electrical charge; electrons have a negative electrical charge; and neutrons, which have no charge. Protons and neutrons are packed into the nucleus, while electrons spin around the outside. The number of protons is what gives an atom its chemical identity. An atom with one proton is an atom of hydrogen. One with two protons is helium, with three protons is lithium, and so on up the scale. Each time you add a proton, you get a new element. Because the number of protons in an atom is always balanced by an equal number of electrons, you will sometimes see it written that it is with the number of electrons that defines an element. It comes to the same thing. But this was the way it was explained to me. So, up until this point, all right, these are things that the author um, is telling us about, but these are things that we already know. These are things we've already learned about. It should confirm what I taught you, what we went through when we was learning about this atom. So this is something that is confirmed by our reading. That's kind of one of our big three questions there. Then we see this quote at the end of that paragraph there. I did not read it, but it says, "Protons give an atom its identity, electrons its personality." So protons here, depending on how many protons there are, this is what gives the element its identity. Depending on how many electrons there are, this gives it its personality. So when we think about identity, think about personality. We think about identity of a human. This could be our thumbprint, right? Everybody has their own unique thumbprint. This gives us our identity. This is like our proton. Electron-wise, would be like our personality. We would think about our psychology, our character is, how do we rationale things. Do we have a strong temperament, or are we extrovert, introvert? These things such as this. All right, back to the book. So now we're at the next paragraph. Neutrons don't influence an atom's identity. They do add to its mass. The number of neutrons is generally about the same as the number of protons, but they can vary up and down slightly. Add a neutron or two and you get an isotope. The terms you hear in reference to dating techniques in archaeology refer to isotopes carbon-14, for instance, which is an atom of carbon with 6 protons and 8 neutrons, the 4 being the sum of the 2. Neutrons and protons occupy the atom's nucleus. Before we go on, just something to think of, look at. So most of the time we focus on these protons and electrons, and if you remember, something else we learned about is the neutrons. And remember, if we change these, right, we get an isotope. So this element here has 1, 2, 3, 4, 5, 6 protons. So we know it's carbon. 1, 2, 3, 4, 5, 6 neutrons. So right there in the bottom, when it's talking about carbon-14 and isotope carbon dating, it says carbon-14, which means you would need a mass of 14, which is right here. So we need 14 subatomic particles in here. We cannot add protons because that changes identity. We don't want to change the personality because it won't change the mass. So we add 2 more neutrons, and that gives us our isotope of carbon-14. Again, this is something we've learned, should be confirming our knowledge here. The 14 is also a signpost for the stat. So anytime we see that number, we need to stop and make sure we think about that number and what does it mean. All right, now we're at the top of page 141. About to start getting a little interesting here. So, as Copper has put it, if an atom were expanded to the size of a cathedral, the nucleus would be only about the size of a fly. But a fly many thousands of times heavier than the cathedral. It was the spaciousness, this resounding, unexpected roominess that had Rutherford scratching his head in 1910. So this is a signpost. This is a contrast, contradiction, compare and contrast, whatever that signpost is. We're comparing a cathedral to an atom. We're saying if we were to blow up the atom to the size of the cathedral, kind of what you see here, um, kind of what I was trying to demonstrate with this, by kind of shrunk down the cathedral more than blew up the atom. Um, the nucleus would only be about the size of the fly, which is about what we got here, a little bit bigger than a fly. But it would be thousands of times heavier than this whole entire cathedral, which is a pretty crazy thing to think about. All right, back to the book. It is still fairly astounding notion to consider that atoms are mostly empty space, and that the solidity, right, we experience all around us is an illusion. So that word solidity there, what is that even talking about? So check out this. Solidity is like most things that we experience with, that we touch, that we interact with in our lives, is of the solid state of matter. So here you got Peter Griffin jumping off into some solid gold. So our lives, our life that exists within solidity, right? Everything we kind of experience or we interact with is of the solid nature. When two objects come together in the real world, like billiard balls, excuse me, which are most often used for this illustration, they don't actually strike each other. What? They don't actually strike each other. So this is kind of a surprising fact, right? This is kind of one of our big three questions. Negatively charged balls repel each other. So got a lot of order there. So looking at the billiard balls here, so when they collide, this is saying that they never touch. Shocking. Shocking to think about, because our whole lives we thought the balls touch. Okay. Um, Rather, as Tommy Ferris explains, the negatively charged fields of the two balls repel each other. Were it not for their electrical charges, they could, like galaxies, pass right through each other unscathed. Um, let's see. Well, I thought there was a word there somewhere. Hold on, my bad. All right, so we'll keep going. So what's happening here is there's electrostatic forces, and this might be confusing or you're a little shocked or don't understand what's going on, where you have positive and negatives are opposites and they attract. So when you have two electrical charged particles that are of opposite charge, they will attract, as you see, in the upper left GIF. As you see this lady come flying in, she's being attracted to this man. Um, but with like electrons are negative and other electrons are negative. When like charged particles are near each other, they push apart, kind of as you see in the bottom right GIF and the top right GIF. So when two objects come together, it's like the bottom right here, they never actually touch. All right, they never actually come into direct contact with each other. So this is kind of like the analogy of the two galaxies, how they pass right through each other, pretty much unscathed, coming right back into what they look like before after they pass through each other. Pretty cool. What else we got here? All right, we see this word levitate come up. So, and the book says, when you sit in the chair, you are not actually sitting there, but levitating above it at a height of 1 angstrom. So you're not sitting in the chair. You're levitating, kind of like what you see here. All right, back to the book. The picture that nearly everybody has in mind of an atom is of an electron or two flying around a nucleus, like planets orbiting the sun. This image was created in 1904 based on little more than clever guesswork by a Japanese physicist named Hontaro Nagako. Pretty close, I think. It's completely wrong, but it's durable just the same. As Isaac Asimov liked to note, it has inspired generations of science fiction writers to create stories of worlds within worlds in which atoms become tiny inhabited solar systems of our solar system. Turns out to be merely a mote in some much larger scheme. Even now, CERN, The European Organization for Nuclear Research uses Nagaoka's image as a logo for its website. In fact, as physicists were soon to realize, electrons are not orbiting planets at all, but more like the blades of a spinning fan, managing to fill every bit of space in their orbits simultaneously. But with the crucial difference that the blades of the fan only seem to be everywhere at once, electrons are. So think about the blades of the fan that you've seen before, right? When the blades are spinning fast enough, it seems to be the blades seem to be everywhere at once. We know this is not true, um, but they look that way. So this is kind of a visualization of this electron. The only difference is how the blades seem to be everywhere at once. We know they're not. The electrons actually act as if they are everywhere at once, which kind of seems impossible, right? Let's continue. Needless to say, very little of this was understood in 1910 or for many years afterwards. Rutherford's finding presented some large and immediate problems, not least that no electron should be able to orbit the nucleus without crashing. Conventional electrodynamic theory demanded that flying electrons should very quickly run out of energy in only an instant or so and spiral into the nucleus, with disastrous consequences for both. There was also the problem of how protons and their positive charges could bundle together inside the nucleus without blowing themselves and the rest of the atom apart. Clearly, whatever was going on down there in the world of the very small was not governed by the laws that apply to the macro world and the very big. So, kind of thinking about this challenging concept of the electron, we know they continuously exist outside the nucleus, but they should, based on what this book say, behave kind of like the marble does here in this image you see. So after reading this, my thoughts were like this. My mind is blown. These two puppies are trying to touch each other, right? They never will. Right. Challenged everything I kind of thought about the atom and how it worked. All right, we'll continue our discussion. That's it.